Welcome to Algebra 2. Today we've got Solving Radical Equations and Inequalities, Section 5.4. All right, so steps to solving the equations. Well, we've already talked about what it means to have a radical expression, and we've kind of explored how to simplify and work with radicals. But here, if we are dealing with an equation and we want to solve, we need to find a way to undo the radical, or as we've seen earlier, a rational exponent in some cases. And the solution steps are pretty simple. First, we want to isolate that radical, get rid of everything else around it. Then we want to undo the radical, and that involves raising both sides to the appropriate power. Okay, then we're going to solve the result, and it is imperative that we check the solution. Because we're raising sides to powers, what can happen is, obviously, if we take a negative number and square root it, we get a positive result. So numbers are changing value. So it is possible that we have solutions that are showing up in our work and seem just fine, but they actually won't work in the context of the problem. And we'll talk about ways to check that as well as we go through this lesson. Now, if we have an inequality, there are a couple things to consider. With a even indexed radical, we can only have positive numbers under that radical if we want real outputs, real numbers that we can plot on our graph. So we need to be aware of the domain, what's allowed inside. Other than that, we're basically solving it as if it were an equation. But again, we want to check and make sure that we satisfy the radicand, what's underneath the radical sign, in those even indexed radicals. We also have some really nice graphing calculator support. We've mentioned earlier the life hack method to check our work. That's the main thing I was talking about on the last slide when I said we can check our solutions. We can plot both functions and just see how many times, graph each side of our original equation as a function y1 and y2, and then see how many intersections should we have. If we're getting 3 solutions but the graphs only intersect once, then we definitely had some extraneous solutions there. So a lot of support as far as what we can do to be confident in our answer. So here we have the first example, solving each equation and of course checking our solution to make sure it works. Number 4, here our radical is already isolated. It is a square root, and since it's already isolated on the left-hand side, I can immediately jump into squaring both sides in order to eliminate that radical. So I end up with the equation 3x plus 10 equals 64. And if we subtract 10 from both sides, and this is Algebra 1 work right here, we get 3x equals 54. Divide both sides by 3. Find x equals 18. Now I don't want to box that in yet as an answer. I want to check my work first, so I would just plug it back in. The square root of 3 times 18, that's 54 plus 10, is the square root, the positive square root of 64. Is that equal to 8? Yes, it is. So I can accept that answer. Number 12, here we've got another one. This is a 4th root, but it's not isolated yet. So the first thing I want to do is add 13 to both sides. So I have the 4th root of 4x equals negative 2. Then, to undo my radical, to undo a 4th root, I would raise both sides to the 4th power. And I have 4x equaling, let's see, it's a negative to an even power. That negative is going to wash away, 16. We'll divide both sides by 4, and I find that x equals 4. Again, I don't want to box that in as an answer. It seems like if we're moving quickly, it's time to move on. You know, that's what makes these tough on the test. We need to go back and check. So let's plug that 4 back in. Is the positive 4th root of 16, then take away 13. Is that equal to negative 15? Well, the 4th root of 16, again, it's a positive 4th root. That's just 2. Is 2 minus 13 equal to negative 15? No, it's not. So our one possibility, our one hope for an answer doesn't check out. There are no solutions to this. Okay, obviously those are pretty straightforward. You know, we had one radical and it was pretty easy to eliminate. and isolate. For number 18, this is probably the most involved problem from a writing standpoint. You can see our radical is isolated, but there's also another variable on the right-hand side. Well, how do I eliminate that radical that's isolated? I would square it, but if I square one side of the equation, I need to square the entire other side of the equation. This is where students often mess up. What they'll do is they'll just square the x and square the 3, not take that as a whole term together, x plus 3 squared, so they'll miss out on some terms. On the left, the radical cancels just like we want it to, and it's 2x plus 30. And on the right, we FOIL that out. Now, we had talked about earlier in the year, a nice shortcut if we ever have a binomial squared, the first thing squared, 2 times the first times the second, and the second thing squared. Here is a great example of how that can be a really, really big benefit to you. And I'm going to use this shortcut here. If not, take the time and FOIL it out. It's not really hurting you at all. Just, you know, it's going to take a little bit extra time. So we've got x squared plus 6x plus 9 on the right-hand side of our equation. And if I want to solve what's left, look at it. It's a quadratic. So I want to get that set equal to 0, try and factor it. If not, I can always use the quadratic formula. But we do have ways of solving what's up on the screen right now. I'm going to subtract 30 from both sides and subtract 2x from both sides. Since my x squared is positive on the right, I want to move the other terms over to join that positive x squared. That's how I'm going to get it set equal to 0. X squared plus 4x minus 21 is our resulting quadratic function. And look at that, it's factorable. My factors are a minus 7 and a plus 3. Well, why don't I check my work there? It's a plus 7 and a minus 3. So my solutions, again, I'm not going to box these in yet, are negative 7 and positive 3. I need to go back and check. Make sure that works. I squared both sides, so I can't be incredibly confident in that answer right now. All right, so let's see what happens if I plug in a negative 7. Then I would have the square root of negative 14 plus 30. Does that equal negative 7 plus 3? Well, on the left, my radical is the positive square root of 16. Does that equal negative 7 plus 3? Does the positive square root of 16 equal a negative 4? No, it doesn't. So negative 7 doesn't work as an answer. Let's try the positive 3. Here I would have the square root of 6 plus 30, 36. Does that equal 3 plus 3? 6? Yes, it does. The positive square root of 36 is a positive 6, so that works. X equals 3 is my only solution for that. And if we wanted to check, we could plug the radical in as y1 in the calculator and x plus 3 in as y2. And what we should see is a graph that only has one intersection point. One intersection point means I should only be coming up with one solution. All right, how about number 22? Well, here I've got multiple radicals, so how do I decide which one to isolate? I just need to pick one. You know, our first step is to isolate the radical, so I'm going to add this root x plus 12 to both sides. Okay, that way I isolate my radical 3x minus 3. And I also set up something where, hey, look, the other side's an isolated radical as well. That won't always happen, but when it does, it's nice because then squaring both sides of my equation cancels out both radicals. I'm left with 3x minus 3 equals x plus 12. Let's combine like terms. Welcome back to Algebra 1. Subtract x from both sides, add 3 to both sides, and I find that 2x equals 15. Divide both sides by 2. I get x equals 15 halves. And I'm not going to box that in just yet. I want to be sure that when I go back and check my work, that I get a true statement. So first, I've got the positive square root of 15 halves times 3 minus 3. So that's the square root of. This would be one where I'd probably use the calculator for this just because of the mental math is kind of tricky. So I got 45 halves minus 6 halves under a square root minus our second square root, 15 halves plus 24 halves, if I get common denominators there, right, to add the fractions mentally, I want that to total up to 0. Kind of separate that from my possible answer over there. So let's see, my first radical, 45 halves minus 6 halves, that's 39 halves, minus this radical, 39 halves. Hey, I'm taking a positive square root of 39 halves minus a square root of 39 halves. That is going to equal 0. So my answer checks out. And again, we could use the calculator. We have that calculator tips video that shows you how to use calc intersect. That would be a nice way to confirm that their intersection does happen when x equals 15 halves or 7.5. Okay, here is the most involved case. We have multiple radicals, we've got variables on both sides, and not everything is under a radical. So here what we've got is our tough situation. And you can see that it's already set up in a pretty advantageous way for us. We've got our more complicated radical isolated already. If it wasn't this way, we would want to get it set up so that our more complicated radical was definitely isolated. Well, radical is isolated, so to undo that radical, I would square both sides. And again, that means taking the entire right-hand side of the equation and squaring that. That means we're going to have to FOIL something with a radical. That's kind of weird. On the left, we get our cancellation that we want. It's just x plus 2. On the right, we have to FOIL out, and I'm going to use that shortcut. But again, if you're not comfortable with that, use FOILing just off to the side. It doesn't take that much time. First thing squared, 2 times the first times the second. And then the second thing squared is negative root x times itself. So that would be plus a regular x. So in this case, squaring both sides didn't fully eliminate the radical. Oh boy. Well, let's see what happens when we start combining like terms. Now I want to try and isolate this radical so that I can again square both sides. So I would subtract x from both sides. Oh, that's really nice. The x's all, those other x's cancel out. I would subtract 4 from both sides. So negative 2 equals negative 4 root x. Let's divide both sides by negative 4. 1/2 is equal to square root x. Now I can square both sides to solve. When I square a fraction, I square the top, square the bottom, and I find that my possible solution is x equals 1/4. And let's see if that makes a true statement. So here I'll do my check work in green over here. Does the square root of x, that's, we're testing 1/4, plus 2, does that equal 2 minus the square root of 1/4? All right, well, the square root of 1/4 plus 2, that's 1/4 plus 8/4, 9/4. Does that equal 2 minus the square root of 1/4, which is 1/2? Well, I know that when I take the square root of a fraction, I square root the top and the bottom. Is 3/2 equal to 2 minus 1/2? Hey, that's 3/2 as well. So my answer checks out. X equals 1/4 does work. And again, we could check this work in a calculator and see if our intersection point happens when x equals 1/4 or 0.25. So again, multiple ways to check, but we definitely want to make sure our solution is included. Okay, so we've handled the radicals. Those are pretty easy to do. Powers undo roots and vice versa. But what about if we have rational exponents? There are two different ways to approach this. And one is to change that into a radical so you can clearly see what you have to do to each side to undo it. But that involves a little bit of writing, and in more complicated cases, that can really be a little bit of a burden. So we're going to go through how to use our rules of exponents to help us out. This term right here with the rational exponent, that x to the 3/4 power, that's the term that represents a radical. So just like mentioned earlier in this lesson, we want to isolate that term. So I'm going to start by adding 14 to both sides. And then dividing both sides by 2. So 27 is our x to the 3/4. Okay, well, again, seeing this expressed as a radical is going to help us out, but one thing I can do is say, what can I multiply both sides by, or what can I raise both sides to as a power that would clean this up? All right, well, if I raised both sides to the reciprocal power, 4/3, then my exponent would become, right, power to a power, we multiply the exponents. On the left, this would become x to the 12/12 power, x to the first. That's just x. That's what we want. We want to solve for x. So my value x is going to equal 27 to the 4/3 power. Okay, and then of course we want to simplify this answer. That's not an easy thing to plug back in and check, and it definitely looks like a messy result. But 27 to the 4/3 power, remember that's like the cubed root of 27 to the 4th power. And I know 27 is a perfect cube. We've gone through that quite a bit in chapter 4 when we did sum or difference of perfect cubes. We should know that by now. We should accept that as fact. So really this is 3 to the 4th power, or 81. Since that thing inside parentheses, cubed root of 27 is 3, that answer x is really an 81. And again, I'm going to check my work to make sure that raising to the 4/3 power didn't affect my answer at all. But let's see what we get. So 2 times, just plugging it back into the original, 81 to the 3/4 power, and then minus 14. Does that equal 40? Okay, so 81 to the 3/4 power, that's like the 4th root of 81 cubed, and I'm actually going to write it this way. The 4th root of 81, well, we just did 3 to the 4th equals 81 over here, so its 4th root is 3. So I've got 2 times 3 to the 3rd minus 14. Does that equal 40? Well, 2 times 27 would be 54, and then take away 14. Yeah, that would equal 40. So our answer does check out. X equaling 81 answers that question. Okay, and again, a calculator could be a great help as far as evaluating that work. Now, inequalities. We need to be on the lookout. Because of the domains that come along with different types of radicals, we need to be aware of other restrictions that could apply. So we need to make sure that the radical is happy, and then we need to make sure that we find our appropriate solution, that the whole inequality is happy. So for number 40, right away, I notice it's an even index radical. It's a square root. That means negatives aren't allowed underneath. So I'm going to set up a little mini inequality there that says whatever's under the radical, since it was an even index, that has to be greater than 0. And that's something I want to keep in mind throughout the problem. We're going to identify that early. After that, we're going to treat it as if it were an equation. 7 root x plus 1 less than 9. Well, I'm going to imagine that instead of less than, it just says equals 9. All right. Well, here we would subtract 1 from both sides. Divide both sides by 7. Ooh, this is not a friendly one. And find that x equals, when we square both sides, 64 over 49. Okay, and we could go back and check that in the equation that we created up above to make sure that works. The square root of 67 over 40, or 64 over 49 is 8 over 7. Times 7 is 8 plus 1 equals 9. So the answer does check out. We would want to take a second to make sure that works. But now, with our inequality, and again, remember this was a less than the whole time, and we're gonna use checks to ensure that that is the case. But here's what I see happening. I see that 0 is a key point where my solutions would stop. Okay, so I'm going to plot that on a number line, and then this 64 over 49. was another key point. So right now what I'm seeing based off my inequalities, just through solving, I've got x is greater than 0 and x's that are less than 64 over 49. So I'm thinking that the area in between those is going to be shaded. But it's always helpful to know for sure. So I know that a nice clean number that I could check is a 1. I'm going to check and see, is that true in between? So we're going to basically check each of these 3 regions of our number line to see where our solutions happen. So I know that if I plug anything in that is less than 0, I'm going to upset the radical. So I know there can be no solutions to the left of 0. Plugging 0 into the radical is just fine, so that gets a solid dot on the number line. And I know that at this value of 64 over 49, I had a less than symbol, so that gets an open circle on the number line. Kind of tying this idea into solving inequalities that you learned way back in Algebra 1. Now, what happens when I test a 1? If I plug a 1 into that, I get 7 times the square root of 1, which is 7, plus 1, which is 8, and 8 is less than 9. So this middle part actually works when I tested a 1. So I know I can shade that region. And then just to be sure, I'm going to test a number out here, and I'm going to choose the number 4. I know 4 is beyond 64 over 49, so I know it's in that last little section of my number line. If I plug that in, maybe it's true. I don't know. Maybe there's just one place that messes up our inequality. But if I test this point, then I know for sure that the inequality holds. So plug a 4 in, 7 times the square root of 4. That's like 7 times 2, 14, plus 1, 15, which is not less than 9. So I know I do not include that region. I'm only concerned with this. So how do I express my answer? Well, I want all x's that include 0. So 0 is less than or equal to x, which is less than 64 over 49. Since I have a contained region on my number line, I need to use a compound inequality to show that the x is between those 2 values. So there's my solution, and the number line really helped us clarify that. All right, for number 42, here we have an odd indexed radical, which is a relief for us because odd indexes allow negative numbers for inputs. They have outputs all the way across. So if I have this situation, I don't have to worry about making the radical happy. We know it'll work the whole way. We're just going to solve this inequality as is. To undo the cubed root, I would cube both sides. I find that x plus 7 must be greater than or equal to 27. I would subtract 7 from both sides, and I find that x is greater than or equal to 20. Well, I want to be sure of that on the number line, so here is 20. Greater than or equal to means a solid dot, and I'm thinking my solutions are over here, but it might be helpful to check some numbers. I know that 8 is a perfect cube, so if I were to, I don't know, test x equals 1, which would be over here on the number line, if I plug that in, then the cubed root of 8, 2, is not greater than or equal to 3, so I know that numbers to the left of 20 don't work. Right? Well, what about on the other side? I know that 64 is a perfect cube, or yeah, 64, I know that's a perfect cube. So what if I plug in like a 57, which would be way over here? This isn't the scale at all. But if I plug in a 57, which would be to the right on the number line, then I would have the cubed root of 64, which is 4, and that definitely is greater than or equal to 3. So this part of the number line works. That confirms that I should be shading to the right. How do I express that solution? Well, it's the result that I had here. Since the radical did not need any special restraints placed on it, I don't need a compound inequality. I can just say all x's that are greater than or equal to 20. All right. And our last example here in 5.4. An amusement park ride is a large swing. Maximum speed v in meters per second is given by the following radical equation, where h is the height in meters and g is the acceleration due to gravity. They tell you to use 9.8 meters per second squared as an approximation. Determine the height at the top of the swing when the maximum speed is 15 meters per second. All right, so very typical standardized test type question. They give you some weird formula, and you just need to know what you're solving for and what to plug in. So we know that 15 meters per second is his maximum speed, his velocity, I guess, they're using v for. That equals the square root of 2 times 9.8 for our acceleration due to gravity, and we're solving for h, the height of the top of his swing. Okay, well, here what we're going to do, we've got our radical isolated. We want a variable to come out from underneath the radical. We're going to square both sides. So we get 15 squared, 225. That equals 2 times 9.8. Man, that's almost 20. 19.6 times h. And we'll divide away that 19.6. Clearly, they want a decimal answer here, so give me 1 second to power up the calculator and see what that would be. 225 divided by 19.6, 11.48. So that h we were looking for is 11.48, and our units for height, meters. Pretty high up there in the, consider that's pretty close to 40, 45 feet. So pretty tall swing. Here's a look at your homework assignment for this section.